speaking with us today from Helmholtz Institute Framework of Resource Technology. And Richard Gloaguen got his PhD in France, I think. And then he has been working in Germany in different universities, and currently he's head of his group for leading the exploration work applying various spectral imaging. So today he's going to introduce the work that has been done in his group. And so with that, I will give the rest time to Richard, and please leave a little bit of time for our audience to interact with each other. And as we communicated before, we're going to record this talk and then post it on our YouTube. And I'm also going to share the YouTube link to you after the talk. Okay, with that, welcome, Richard.
Yeah, thank you very much for the invitation to present our work. So today we'll talk about innovative exploration, mostly using hyperspectral imaging, including machine learning. And yes, so first of all, a short introduction of our department. So we have four groups in the department. The one is developing sensors. So we develop mostly spectroscopic sensors. So we have developed a laser-induced fluorescence sensor. Now we are developing a Raman sensor, but also platforms like drones. So we have a group working on digital processing because we need to be able to process the data coming out of the sensors. We have also a quite large group of machine learning, and we also try to find innovative applications for all these processes. So today I will talk about the need and what is important is in innovative exploration. So there is a paradox. Right now, we try to go to a more renewable source of energy and reduce our demand in mineral resources. But the problem is that the more renewable energy we need, the more resources we need, and the more diverse these resources need to be. That's one aspect. The second aspect is that that's the demand. The problem is that there is quite a strong reluctance from many stakeholders to accept new mining projects. I'm pretty sure that's the same in China as well. So if you want to have a new mine, it's getting more and more difficult. So we need to have more acceptable ways of doing exploration and doing mining. And today I will focus my talk more on the exploration side, but it could be also applied into extraction. And so what we want to do is to have an exploration that is relying more on remote sensing approaches and to have less people on the ground and less disturbance of the environment and the local population. So the concept is this one. We want to have a multi-scale approach. So starting from satellite airborne data and bridge a gap to ground information. And for that, in the last few years, we have developed quite a few technologies based on drone platforms, but not only, as you will see. So the idea is to combine data at different scales, multi-source, and even in the future, maybe multi-temporal. So airborne data, drone-borne data, ground-based data, and it must be non-destructive, it must be versatile, it must be rapid, multi-scale, multi-view. And all these aspects are nice if you take one out of them and forget the others, but you must have all of them together. And that makes things a bit more complicated and demand new advances in science. And this is what we are looking at. So in the last few years, as you see, we have contributed quite a lot to this because if the exploration with airborne sensors and satellite data was quite established, there was almost nothing on drone, and you will see that it is required because the problems are a bit more difficult and different than with airborne sensing. And we use different platforms, but also, as you will see, information from different sources. So most of our work is based on spectroscopy, but not only. And here I will only describe passive spectroscopy. And here what we use is either the sun or lamps, and they emit a radiation that is either reflected, emitted, or transmitted. And we measure the resulting signal, and we compare to the emission, and from that we can gain some information about what has happened. And most of the time, minerals or the targets will have a specific signature. We call that the fingerprint, and this fingerprint will allow us to identify the target. For that, you can only use a certain band of the electromagnetic spectrum, because most of the energy is absorbed by atmosphere, and there is only one window of accessibility, is mostly in the visible and near infrared or long wave infrared, and then in the radar or microwave, but in between it's very difficult because most of the signal has been absorbed. So we are not working that much on microwave anymore, but it's also a key aspect of remote sensing. Today I will talk mostly about the visible and infrared part of the electromagnetic spectrum. And then when you are doing so, you can use either a point measurement and get some information. So a field spectrometer, for example, will give you this information. But what we are trying to do is go a bit beyond that and use imaging sensors. So you have several ways to do that. So if you start with RGB, so you have 3 bands with a very coarse spectral resolution, but they can have quite a high spatial resolution. The problem is that it's good for all the image processing that you can use, but you don't get that much information about your spectral fingerprint. So it's better to have more information, and most satellite data that you can acquire these days are multispectral. So it means that you have several bands with, let's say, a coarse spatial, a coarse spectral resolution, but also sometimes with a quite high spatial resolution. It's already the beginning to be able to identify rocks on the surface or vegetation, but it's still not sufficient to really characterize your target. In order to be able to characterize your target, you go to hyperspectral imaging, and here you split the electromagnetic spectrum in dozens or hundreds of bands. And it means that you have 2 information. You have an XY information, but you have also a spectral information that allows you to really characterize your target. And if you are lucky, you can image over the entire infrared spectrum. So starting from the visible through the shortwave infrared, the long-wave infrared, to the long-wave infrared. And in this case, you will be able to identify a lot of alteration minerals, but also rock-forming minerals. So if you see in this table that if you look at the entire spectrum, you are able to identify most of the important minerals you can find at the Earth surface. And then if you have that, you are able to really identify your minerals in rocks at different scale, and that from the distance without destroying your target, which is also quite important sometimes. The problem is that the platform has an effect, and the position at which you acquire your data as well. So you can understand that if you are on a satellite and you have a nadir viewing, you will not be affected by as many parameters as if you are on a drone that is a moving platform very near to your target and not at the same position. And that is the main problem we were faced with when we started because none of these procedures were taken in account in the processing routines that were available so far. So you have to correct the data radiometrically in order to get a really true spectrum, and you have to correct your data spatially because it's not anymore a 2D problem, but it is a 3D problem. It means that you have really to identify the structure of your target to be able to position your measure. So, and an example to show you that, so that is a hyperspectral data set that we used in Finland. It's a mine for phosphorus in Silinjärvi. And here in this case, we were not interested in the phosphorus, but in the apatite that they have there, there is a lot of rare earths, and we wanted to map the rare earths. So the first good news is that, yes, we are able to map rare earths with these remote sensing techniques. As I told you, some minerals and elements have a very specific fingerprint, and in this case, the rare earths are very good for that. And then you can produce an image and map this information at the surface. So here it's a mine pit face, and it's a vertical, more or less, outcrop. So in a 2D image, then you're starting to get some information. The problem is that the Earth is not 2D, but is 3D. And at this scale, it's getting extremely relevant. And it means that if you look at this same data set in 3D, you see that you have a totally different perception of what is really going on. And if you would use 2D image processing routines, you would have problems because most of the time, let's say the raster implies the neighboring. So it means that 2 pixels that are next to each other should represent 2 targets that are each next to each other on the surface, which here is clearly not the case. And you can understand that it will lead to problem if you wanted to classify or process this information. So it's very important to keep in mind that it is a 3D problem. So we developed these routines, as you saw previously on this slide. So we have published quite a few papers on that, and now we are ready to produce a product like that, where you have a 3D point cloud. So here it looks like an image, but it's really a point cloud with billions of points. And each point is characterized by an XYZ position, but also an attribute. And this attribute can be multiple. It can be an attribute because it's taken from an in situ camera, but it could be a drone, it could be an airborne information, it could be a satellite information. And because it is non-projected, it means that we can combine this information together. And if you want to go into machine learning later, for example, do data fusion or integrate several data sets to enhance your product, then you see that it is the only way to go. And here's that's an example of a classification using multiple source of data from different platforms and in a single way, and that is the main output of this job. So you can go even further, and I hope it works. Yeah. So once you have this data, you get an additional information. So what we call a digital twin. So it means that before you go to the field and do your experiment, before you send a geologist, then you have this information in a real 3D environment, and you can use virtual reality to test your hypothesis. And because it's really 3D, you can merge that with subsurface information. And instead of having multiple tools to visualize and work on your data, you have only one tools is your 3D visualization or processing software, and you are able to do so. So the main output of that is that in order to get hyperspectral information correctly, you need to correct for all this information, and the errors that occur on your hyperspectral data are really 3D. So you need 3D information. So, but at the same time, because it's 3D, it gives you also a lot more information that it would be a 2D problem. So that's the main take-home message for this part of the talk. Let's see what we can do else with hyperspectral imaging. So, and I will take the example of drill core scanning to do so. If you have kilometers of cores to log because you are doing exploration, it's usually time consuming. It takes a lot of time for people to log these cores. And it's also subjective. It means that each geologist has his own way to log the cores. And even if you have a strong, let's say, strong constraints, you still have variation from people to people. So it's very subjective, and it's very inefficient because you cannot go back to your data anymore. So you would have to take your course again, look at your course, and proceed from there. So you have no archive of your data. It's not a data set per se that you can use. Hyperspectral imaging, and on the other hand, is unbiased. So you don't need a priori knowledge. It's just really a physical property of your rock that you will measure. It's very fast. We can measure up to 1 kilometer per day with hyperspectral imaging, and it's really a data set. Yeah? Like you have a data set for geophysics or geochemistry. Now with hyperspectral imaging, you have also a data set for your core logging, and it looks like that. So we put the core in a tray, and then it goes through the imaging sensor, and then you can map your information. There are still some challenges, of course. As I told you before, we can only map spectrally active minerals. It's only if you go to the state of the art is you will provide spectral maps, and the spectral maps are not directly linked to the lithology. So you will know, for example, you have chlorite. You will know that you have muscovite, but it doesn't give you any information about your grade content. It doesn't give you information about your lithologies. And that is a bit of a problem, because if you want to use hyperspectral imaging these days, then you need to have a spectral geologist in your team, because otherwise you will not be able to implement this information. And then one of the major problems is that the delays. So usually when you map your core, so you send them to a company, and they will provide you with the results when they have processed all the data. Usually it's in weeks or in months. And those are the challenges that we wanted to address. In order to improve and augment the number of minerals, then we need to go to multi-sensor imaging. I will show you an example. In order to provide geological relevance, then we use machine learning, first of all, to process and pre-process the data, so denoising, code registration, using smart libraries, doing feature extraction. But then we go into interesting stuff, for example, super resolution, fusion, and supervised classification. And I will show you one example of that. And the last challenge we wanted to tackle is real-time processing. We want to have information as soon as you get the data. And that is something that is very important. So let's start with multiple sensors. So here you see one of our experiments, and you see the drill core scanner. And if you look carefully, you will see that on the left-hand side, you have here this black camera is a long wave infrared camera. The orange one here in the middle is a mid-wave infrared camera. The big one here in gray is a short-wave and visible camera. And here, a little bit hidden, is a very high-resolution RGB camera. And all in all, it takes 1 to 3 minutes, depending on the number of sensors that you use, to scan a tray of here 4 cores that are about 1 meter long. So, and then you get a data set like that after some processing. So you have very near infrared data, SWIR, data, mid-wave infrared data, long-wave infrared data. And for each point, because they are co-registered, you can get a spectrum like that. And it's very important because sometimes you have extremely complicated mixtures of minerals. And here it's one of the case. If you look at these core data here, you will see that here's the blue minerals mapped in the shortwave infrared, ammonium minerals, so ammonium halite and smectite. And you see that at the same position, you have also a rock-forming mineral. Here in this case, it's albite. So you have a very intimate mixture of these minerals, and you would not have been able to map those with one sensor. And that's really the power of using multi-sensor approach. And then I told you that would be the state of the art. Right now, we will also from now on, we'll talk about what is new, what is innovative, what we do new in our department. And I think we are at the forefront of the research in this case. And here, the first approach is non-supervised learning or semi-supervised learning, where you don't have that much information at the beginning, but you can still use some clustering approaches to get more data from your hyperspectral data. And what I will be talking about today is then a more, let's say, efficient way of looking at hyperspectral imaging is using supervised learning. And then you will be able to produce the maps, not only of your minerals, but of lithologies that are relevant to your for the geologist. So the first example is resolution enhancement, and that is the effect of two information. The one is that, as I told you, it's multi-source. So, and here in this case, we have a very high resolution, very high spatial resolution RGB camera, but with a very low spectral resolution. At the same time, and co-registered, we have lower resolution, a lower spatial resolution hyperspectral data, but with a much higher spectral resolution or spectral content. And the idea here is using machine learning techniques to fuse this information and get the best from two worlds. And here you see the result before and after fusion. So you have the RGB here, the original SSI, so the hyperspectral imaging data, and you see that it's much coarser. And after, we have the spatial resolution of the RGB and the spectral resolution of the hyperspectral imaging merged together. And that is really a powerful instrument, because not only you will get more information about the fine scale structures, but because you have more spatial resolution, you will also get more spectral variation into your enhanced data set. And it means that you will find minerals that you oversaw in the hyperspectral data without enhancement that are in your enhanced data set. The other aspect that I wanted to introduce to you is the real-time processing. So it's very important to get information as soon as possible. And here we use also machine learning approaches to map the cores as soon as they are scanned. And here it takes a few, it's not real time exactly, but it takes a few minutes in order to get your classified maps and get your information from your cores. And it's very important for one reason, is that we can go even one step further and use this information to add value to your product. And here in this case is using augmented reality. Yeah, think about it. You scan your core, and then almost instantaneously, you can provide this information to geologists. And in this case, we use augmented reality. So you get an information of the mineral maps that you have on your core, and you can identify zones of interest where you need further information, and you can really get and pinpoint an area of interest and get, for example, geochemical information on this precise spot. So that would not be possible if you would not have a very fast processing of your data and be able to provide that to the geologist while he is on site to proceed with some additional information. And usually it takes months until you get your assets back to be able to get a similar information. So that it's a huge progress. The next step is, of course, this information, again, is not 2D, but it's 3D. So you map them in 2D, but you have to project them back into 3D. And you can do so if you have the information about the drilling, and then you can put them back into a 3D model and use this information as if it would be geophysics or geochemistry. So you can, for example, interpolate this information. And I will show you that it is not quite simple because those are categorical data. So not continuous data like concentration, but category like it is a quartz or it's not a quartz. And you cannot really interpolate this information, but there are ways to do something similar. So the example I wanted to show you is a case study that we used to demonstrate that it is working. So we went to Spain and we scanned in a few weeks 7 kilometers of cores in a very complex area. It's those are dark rocks, mostly volcanics, and we took 24 samples for the training, and we used electron microscopy and mineral liberation analysis to produce mineral maps at a very, very high resolution to train our models. So how did it work? So we mapped the cores, and in some parts we have both the hyperspectral information and a very, very high resolution mineral information taken from electron microscope. And we co-register this information. From this co-registered data set, we use a dictionary learning. So it means that what we do is we keep the variability of the information into context, and we use that to better classify the information. Why do we have variability? Because here we have a data set with just a few nanometers resolution. And here we have a data set with a few millimeters resolution. So it means that a pixel, a hyperspectral pixel, would present hundreds of pixels in the MLA data. So it means that one spectrum is representing a mixture of minerals. And if you don't take that into account, then you will think that you have only one mineral, but it's not the case. It's a mixture, and you need to take that into account. And that's the power of machine learning. And then, because of that, you are not only able to map minerals, but also to map abundances. So you will know what is the abundances in certain minerals. And because it's a supervised learning, you can even map minerals that are not visible with hyperspectral data, but because they are always in association, you will be able to infer the presence of these minerals. So this is the two really big powers of machine learning. And again, then you can back project this information into 3D. So it looks like that. So here you have hundreds of cores core boxes that represent one core in this case. And then you can plot your information along the core. And you see here that we have a very, very strong correlation of certain minerals with your ore. And that's the reason why we use those as proxies to identify your ore. So here, siderite to identify the methyl sulfide. It's even better because if you understand now your mineral maps, you can see that even if you don't have information about the ore hosting minerals, you have what we call pathfinders minerals. And here in this case, you see that bounding the siderite, you have always an increase of chloride. So it means that if you can map your chloride and your iron-rich chloride, you will be able to generate an envelope of your ore body. And it's what we did, and I will show you so. So it's a place in south of Spain. And as I told you, it will back project information in 3D. And then here in yellow, in blue, sorry, we mapped the amount of ferric chloride, and it gives you an envelope. And because it gives you an envelope, you are able to really pinpoint where is your ore body. And we can compare it with information that was really taken from the mine. And here we can compare it with the ore body mapped by the mine, which is plotted here in red. And you see that we have a very, very nice overlap between what we inferred from the data and the reality. So again, demonstration that it is working quite well. So that was the case of drill core scanning. I will show you that it works at other scales as well. So here's an example in Namibia where we are mapping lithium-bearing minerals. So that is a pit. And the first step, as I told you, is to get the 3D information. And you see here that it is a 3D problem. It's not a 2D problem. And no matter what you want, you will have to take this information into account. Here in this case, we didn't use MLA as training data set because we didn't have that. So we use additional information. And here we were able to have a few core data and also a few hand samples taken from the mine. And we use that as a training. And here you see that we are able to map here what is represented on the left-hand side in green, which is a cookite. It's a mineral that is hosting the lithium. And we can try to find out and document in which mineralogical system it is found. And here you have data from the long-wave infrared, and you see that most of the time, the cookite is associated to quartz. So we have a quartz-cookite mixture. And if you look at the spectrum, because it's very, very, very important, you see that the spectra that we found in this place. So here, that would be an average of 21 pixel of what we thought was a quartz. And here it's a library spectrum from a reference library. And you see that you have a very, very nice match. And if you want to go to amblygonite or cookite, and you will see that you have a very, very nice overlap of the spectral features, and that we are quite confident that we are mapping the right information. And then you can do, as I showed you before, you're able rapidly to map this information. And here, that would be a map of the cookite. And we want to validate that. So you use, here in this case, a LIBS instrument. So it's a laser-induced Brechton spectroscopy, and here you generate a plasma with your laser, and you measure let's say the photons coming out of this plasma to identify the minerals. And here you see that there is a very nice match between the mapped cookite with hyperspectral imaging and the validation using the LIBS. So we can change the scale. Now we go to the hand spectrum and to the hand specimen, and you see that again we find the same spectral signature. So it means that we're very confident that we can map these features and go to the next scale, and here map the amblygonite, the montebrasite, and the cookite at the outcrop scale. So, but that means that we have a fully corrected data set And that this data set is, again, not a 2D data set, but a really 3D data set. But so here you see the results of it. So that is another scale. I wanted to show you in the next maybe 5 to 10 minutes that we can use drones as well. It's a bit more complicated, but it's the same. So we developed platforms for magnetics. I will not talk too much about magnetics, but it's also quite important because you need some subsurface information and not only surface information. So we developed our own drones. Here it's our Gloaguen. So it's quite big drone to carry a full sphere camera. It has a payload of 10 kilo for 20 minutes. We use a fixed wing drone to do photogrammetry. So it's extremely lightweight, but quite fast and can survey quite large areas rapidly. And with that, we can go to the field. So that is the Gloaguen in one of our test sites. And you see here the sphere camera. And the sphere camera with the batteries and all the additional required devices is a payload of about 7.4 kilos. So it's quite a lot. And here you see that we need also a gimbal. The gimbal is there to stabilize the camera because a drone, no matter what, will always be unstable while it's flying. And then you need to reduce all the vibration and the movements in order to get an image. And you will see that it is not trivial. So again, as I said, it is a 3D problem. So those working with spectroscopy will know that the spectroscopy is depending on the bidirectional reflectance. And it means that it is a function of the incidence angle and the measuring angle. And if you don't take that into account, then you will have quite large errors. And here, because we took 2 images with clouds and without clouds, we are able to estimate the effect of this angle. And you see that it is quite a non-neglectable effect that you have on this image. So you need to be able to correct that. So we have developed a toolbox called Highlight. It's an open source software to do exactly that. And if you want, you can download this toolbox. So it takes several kind of information into account. First, as I told you, is the geometry, but also the light source. And here you see that it is important to take that into account because it has a huge implication onto your reflectance spectrum. So here on the top, you see your light spectrum in sunny conditions, and on the bottom, you see the light spectrum in cloudy conditions. And you see that the source of radiation is totally different with or without clouds. If you don't take that into account, you will not be able to retrieve this information. And you see that if you don't take into account that it is a 3D problem, you will have effect like here, where you have shadows. You will have effect due to this BRDF effect that you need to correct. And after correction, you see that you have a much better representation of what is really at the surface. We can even estimate the error. So without correction, you would have a residual of 10%. And if you are looking at let's say spectral features like the carbonate feature, so to determine calcite to dolomite, if you have 10% error, you see that you will not be able to do that. And after correction, we have an overall error of about 4%. And in most places, you see that it is a lot less than that. And that is something that is we to take into account. So I will show you an example of acquisition that we did in operational conditions. So that is in high mountains in the Alps. And you see one of our pilots is here and an engineer making the flight plan. And I will show you a video that shows that it was not easy to acquire data there. It was very windy. We had 12 to 15 meters per second wind. It was quite cold, and we had to protect the drones for the landing and the start. And that's the reason why we are in a little depression. But after a while, we can start, and you will see that the gimbal is compensating for the movement of the drone. But if it's getting too windy, it's a bit too difficult. So we had some difficulties in this area, but at the end we were able to acquire data. So, and then you get a data set like that. So you have your platform moving, and because it's a line scanner, you generate your image by the movement of your camera. And as I told you, without correction, it looks like that. So you don't see anything. You see all these variations are due to the movement of the drone. And you see that if you don't have a 3D corrections, you will not get anything. After correction, it looks like that. Yeah? So it means that at least on this figure, you can see that you have a very, very strong spatial coherence. So we retrieve the spatial variability of the terrain, but it's not enough. We need to make sure that we have also a preservation of the spectral content. And here you see in gray, those are the spectra taken on the ground. And in colors, you have the spectra taken from the sensor mounted on the drone. Just to inform you, because it's only a part of the spectrum that is relevant here to map the calcite and dolomite, so the carbonates. So it's only, as you see, 200 nanometers, and we take about 2000 nanometers when we map the entire spectrum. But you see here that we have a perfect match in the position of this spectrum, which is important. So some of you might wonder why the shape is a bit different. There is a very simple explanation for that. Is the pixel size taken from the drone is about 10 by 10 centimeters, and the point measurement is just about a few millimeters. So it means that we cannot directly compare. What is important is that in this area, the position is identical. And because we have a perfect match in the position, then we can map these absorption features, and then we can estimate the amount of calcite versus dolomite, which is a very interesting topic for the oil industry right now. And here you see a map of those, and you see the spectra here, and you see that there is quite a good constraint on the position of the spectrum, and we're able to map these features quite accurately. And on top of that, we had in situ validation, and we are quite confident that we have the data. Just a few seconds to show that we are not only doing hyperspectral imaging, but also subsurface geophysics. So right now we are looking at MAG, and here it's one of the drone with the magnetometer, but we're also looking at radiometry, and we try to get this information, to get some information about the subsurface. One example was in Norway. It was a very difficult test area because those of you aware of magnetic will see that over just a few hundred meters, we had up to 25 microtesla changes, which is a problem because, as you know, drones orientate themselves with a compass, and here the compass was really struggling to get information because you had so big changes in the magnetic strengths here in this array. But still, we were able to map quite interesting anomalies and demonstrated that even in harsh conditions we can do so. So what is the future? So right now we have started a new project where we want to acquire all this data at the same time, but adapted to each method. So You will not fly a drone with a magnetometer like you will fly a drone to do photogrammetry. You will not fly the same drone with hyperspectral imaging and so on. So what we want to have is a swarm of drones working together and updating each other in order to acquire just the data that is required, but all the data that is required to discriminate the site. That's a project which started in collaboration with several institutes, and maybe in 1-2 years we will be able to report on that. So thank you very much for your attention. I think I'm still on time. Again, I wanted to reiterate that it's not only my work. I'm working with a wonderful team, and here you see part of them in the field where we try to get acquiring some data and validation in Spain. Thank you very much, and I'm happy to answer your questions if you have some.
Okay, thank you very much, Richard. Now it's a question from our participants. So feel free to open your mic, ask a question, or you could post your question in the chat and I could read the question on your behalf. So go ahead.
Hi, Richard.
Yep.
Thank you very much for the very interesting talk. I'm a geophysicist, so I'm quite interested in actually the large part of the presentation. So could you share your thoughts on how you can integrate the geophysical data, say magnetic, with the current, like the workflow you guys developed, like mainly, I assume it's spectral data, right?
Yeah, so actually we have two publications on that. So one is in the site I showed you before in Siliniavi. So we use, I can tell you one workflow where it works quite well. So you can do forward modeling with the magnetics by constraining your forward modeling, getting the information from the surface. So you map your surface and you know what kind of lithologies you have. If you are lucky, you get some information about your magnetic susceptibility, and then you can do a constrained forward modeling. So, and it means that you have a much better chance to get the right model. So that's the first approach we used. We have a paper as well in Greenland where we did inversion. And here again, the inversion was constrained by the structure and the spectral information that we got. So here the idea is to constrain much better your subsurface geophysics by using the surface information.
Yeah, it's very interesting. I'll probably direct your suggestion to my colleagues in Cicero, Australia. They're actually quite interested in mineral exploration.
Okay, next question, please. Okay, the first question was from Yifeng Chen from Zhejiang University. Actually, I have a relevant question. So, Richard, when you show your different scale of this samples that you get the spectral images, I didn't recall that. Maybe I missed, but I didn't recall that to see the scale like the scale of a microscope or scale of the even from hand lens from thin section. I think that's another way that you could tell the mineral mold, for example, in the core drilling core. Is that right?
Yes. But if we do supervised learning, it's exactly what we do. So here it's not exactly a thin section that you see here, but it's an electron microscope data set. So using MLA, but you can use ChemScan, you can use different mineralogical approach. So what you get here is a mineral map that is with maybe 20 micron resolution. And what we do is we co-register this to the hyperspectral data. So of course you have quite a mismatch in scale. And that's the reason why we use this dictionary learning in order to preserve this information. So we can call it noise, but we call it useful information. And that's the reason why we use that. So we are using that at a very small scales. There is something that we don't do is to use hyperspectral imaging on a microscope, for example. That's something that we could do, and we are thinking of it actually to mount a camera directly on the microscope. The problem is that most of the cameras that are available are line scanners. So it means that you have only one line, and in order to be effective on the microscope, you need which we call the snapshot camera or full frame camera. And so far, the only cameras we know that are full frame are not acquiring the full sphere. They stop at around 1,500 and 1,700 if you're lucky. And it means that you don't get the full spectrum. So it's a very valid point, and we hope in the future that we will be working in this direction, but it's a bit problematic.
Okay, thank you. So next question, please.
Well, could I ask another one? Hi, Richard. I'm actually also quite interested in essentially all this kind of method workflow applying to either the drill core or the pit mine. But for mining exploration, it's quite challenging, at least in Australia, is this undercover exploration. So do you have any suggestions, ideas on how you can use the current workflow and apply to potentially undercover exploration?
Yeah, so it's a very valid point, and it's something that I tend to overlook or not to mention. It's right. So these techniques, at least the hyperspectral techniques, only work if you have outcropping minerals. If they are covered by vegetation, soil, or even a cover, then you will not see it. That's to acquire. So geophysical sensors. So the first one was MAG, but we're also working with radiometrics, and soon hopefully with EM. So we will have a test with EM in March. But those are geophysical methods, so they are not really direct measurement.
Okay. Look at data fusion or joint inversion is the direction to go.
Exactly, it's what we are doing right now. Is to do that. But again, you need to find the right information, and it's one of the main problem with these approaches is that if you don't have the right input data, then it's difficult to get added value. Yeah. But you are right. It's something that we need to look at.
Okay, true. Thank you very much.
I have another curious question, not exactly in the techniques part, because in your talk that you show the VR, etc. As far as I feel, not that I know, is that it's still quite expensive, to use VR. I said, what other people use it for games, etc. I think it's still a while before it is fully available at a very low cost. So from the cost perspective, that what's your vision for it? That how long it will take for geology, for example, in the future, for really could go in the field just in the room using VR, as what you have shown that happening in the lab that you have been you have been leading.
Yeah, it's a very valid question. And when we talk to mining companies or other companies, we have a different approach, because here you are talking about operational costs. The problem is not the operational cost. At this stage, you are right. It will be always cheaper to send the poor geologist on a very dangerous slope because he's paid 20 euros per hour if he's lucky. The problem is not that. The problem is the risk. how much will it cost to the company to have a casualty or an injury on site? Because if you're on these slopes, of course, the risk that this person has an injury, but you have also the risk that there is a rock failure, a slope failure, and so on. So the risks are quite high. The other aspect is that you are not only buying the information at one time, but it's also part of your archive. And think about it in terms of not only spatial information, but also temporal information. If you would take that 3 times, 4 times, 5 times every week, then you would get information that is a lot more relevant. For example, if you're looking at your mine phase, you can measure not only volumes, but specific volumes of interest. So you can estimate your mine waste, you can estimate your ore, and so on. But you can also estimate, in some cases, the amount of clay minerals. And we know from at least 3 sites where we have been working that they didn't listen to us, and they didn't take this approach and had massive rock failures. So there is one site in Africa, in South Africa, one site in Namibia, and one site in Spain, where they had massive failures of the slopes. And then, of course, so the cost of sending a drone and to take multiple data would have been expensive, but the cost of having a massive failure in your pit there is no comparison. So you have to take into account also the long-term risk and what is the added value to your workflow.
Okay. Yeah. I think there is no doubt that it is just a matter of time when this is fully implemented in almost all countries. So even in China, it is active field for the mining site to run the autonomous driving, because that's a perfect site where you don't have the cost running around, and also it's a job that attracting less young people to go to, because young people prefer to work in urban cities. And if we could make that, like say, the being geologists that in the laboratory and working more efficient way, that definitely that will be a more attractive job. But yeah, I think it's just a matter of time. I don't know that when will that, I say this rising cost, hard to attract a new generation of geologists to the gradually decreasing cost of what we are doing, because in the end the VR cost will it has become cheaper and cheaper. It's just a matter of time when this really converge.
But yeah, but actually it is time right now. So you see in terms of operational costs, because we have also a company doing this kind of work, to drill 1 meter of core costs you in Europe, not only in China, but in Europe, between 200 and 300 euros. So that is the cost per meter of drilling. The cost that we have per meter of processing, delivering this map almost in real time, is about 30 euros per meter. So you see that those are minimal costs compared to the drilling. So if you invest in drilling up to 200 euros per meter, it would be silly not to invest a few euros to get a lot more from your data. And that's the same for your mine. To acquire a few hundred square meters with a hyperspectral camera now with a drone, it's really nothing. It's less than to operate one of these big trucks that to transport the ore per hour, a lot less. So it's right now, it's not the condition why it is not used is not the cost factor. What is the reason why it is not used is that so far it has not been accepted by the sector as a valid tool to streamline their operations. So the mining sector is extremely conservative. They never change things if they are not obliged to change things. But in many other sectors, drone operations have overtook the manual operation. So if you do survey of electrical power lines, of bridges and whatever, now it's done with drones. Right? There is no doubt about that. And we are talking about the same cost.
Okay. Thank you very much, Richard, for your talk and for interaction. So it's a broaden our horizon on this topic, and thank you again for giving the talk, and thanks everyone for your participation, and see you next week.